two meetings, or one meeting, 2 halves, or whatever, was really, is that going to support me? Yeah, it's good. Was to talk about this subject of conversion, and therefore it was great to have Peter, you both, to talk about some of the detail, if you like, the scientific detail of theories that actually supported these idea of convergence between the various subjects. And we are aware of quite a number of undergraduates and people of, if you like, the next generation, doing all sorts of different subjects, not necessarily doing computing. And it'd be interesting to discuss some of the ideas that flow from this idea of convergence. Because the more we look at it, the more it appears to us that computing, which we invented, and biogenetics, which I suppose if you take DNA, was more or less, if you like, discovered, if that's the right word, roughly at the same time as the beginnings of computing, and cognitive neuroscience, which I suppose has been going for, Peter, you mentioned Raymond Cageal was the first person to actually isolate a neuron and so on and so forth, and that's about 120 years ago, I think. But it was a subject that was out of fashion for a long time, and only really in the last 10 or 20 years there's a huge amount of effort gone into trying to understand this thing out here. We've always rather thought that in computing, it started its life as we all know, to a certain extent, in electric power. And most people for the first 10 years thought of it as mathematical boxes for mathematicians to play with. And I suppose, really, if you think about it, that's what it's been used for most in the last 50 years or so. But we had a lot of us, I think, had a feeling that there was an awful lot more to computing than just running banks, accounting systems, or credit cards, or even really complicated things like air traffic control. And we've learned that we've been able to use computers for more and more and more and more. And that word disruption, we've disrupted an awful lot of industries. And it's having an ever greater effect. And we're very conscious that the media is all full of horror stories. Hollywood, of course, rather like a disaster, some dreadful computer that's got loose and is going to destroy the world. And will the Saviour get there? And there's only 5 minutes, 4 minutes, 3 minutes, will he get there? I mean, that's all good stuff. It's all a load of rubbish. And all this business of artificial intelligence, which has come and gone over the last 50 years, there are people going around talking about the possibility of computers getting so intelligent, they're going to take the world over. I think it's always going to be in 20 years' time, isn't it? And it's still another 20 years. But there are really quite senior people in the scientific world talking about, actually, if we aren't careful, computers will get cleverer than us and end up we'll be the slaves and all this sort of stuff. It's also dreadfully pessimistic. And I can't help but think that doesn't really help either ourselves in science in the way, well, computing specifically, it doesn't really help the whole community because it worries people. And especially if you're not too sure if a computer might take your job over. Any of you that came here by taxi, no doubt, as soon as you said you were going to British Computer Society, you got an earful of what Uber was doing to them. And that's another subject. But there are lots of people who are not sure if in the next 5 or 10 years, they'll be told that actually a computer's doing your job now. Which is very difficult. The Bank of England, no less, are actually quite worried about this. They actually asked the Real-Time Club, which is quite a surprise really, to the Real-Time Club, to write a paper on the economic consequences of the computing revolution. For those of you who didn't know economics, of course, it was taking the words of famous remark, the economic consequences of peace. I hope everyone in this room knows who wrote that. Because they're saying, yes, computers may take over an increasing number of jobs, functions, and that sort of thing. But there's another aspect to this. It takes away their purchasing power. Now, at the moment, it's very clearly obvious that absolutely nobody has the faintest idea of what's going on in the world as far as economics is concerned. I'm not just suggesting the Treasury in this country, but very clearly the Treasury in the equivalent of the United States. There's absolutely nobody in Europe who's got the faintest idea of what's going on. Japan, as you know, has been in a recession since 1990, and they've tried everything in the book: dear money, poor, cheap money, free money, collecting money, etc., etc., etc. It's had no effect. And we appear to be following them. And so it actually becomes quite a problem, because maybe what's happening in the computer world is reversing what was created in the Industrial Revolution. The Industrial Revolution was all about taking an agricultural community that didn't bother with money, but if anybody earned a bit of money, there was nothing for them to spend it on. And it created people and jobs and purchasing power. And so the whole of economics is based upon that. Now, if computing is gradually taking away that purchasing power, that presents some really serious problems. So there's a lot of people going around and being a bit pessimistic about this. Well, the Real-Time Club is a bunch of entrepreneurs, and as you know, entrepreneurs are exactly the opposite. I mean, we're all optimists. As far as we're concerned, you know, the remark about whether something's half full or half empty. As far as we're concerned, it's full. Certainly not just half full. And it therefore struck us it would do too much harm to start talking about the enormous potential advantages that computers are bringing us. And that's the genesis of a series of meetings we're planning and wanting to hold. A word or two on the two subjects of biogenetics and cognitive neuroscience. Because I don't need to repeat everything we were talking about this morning. It's very clear that the computer is not a brain, and then suggested it was. It was probably a bit of a shame back in the 60s that people started using the word electronic brain, because that put everybody off. And of course it isn't. But the actual architecture is remarkably similar. And we've been talking outside this room today. Computing doesn't necessarily give us answers, but it does help us ask questions. How does this work? How does that work? And by looking, as we can, at our computers, because we should tell you, we can see how we organize information, how how a computer remembers or memory. It helps us think about what do we mean by meaning. We can talk about the various aspects of it, and then try and say, the computer does it that way, how does this do it? And that's very helpful. In biogenetics, we've got a quite remarkable memory system. And you've all seen recently, literally in the last few days, there's this way of actually looking at DNA, seeing CRISPR, and the P stands for palindrome. It is now possible to divide up the gene into small pieces. We can now actually begin to read DNA like you read a program. And if you can read it, you can edit it. And the implications of that are pretty dramatic. Very big questions if we can use this wonderful technique to cope with illnesses of hereditary illnesses or else for another one. But can we make changes that make people more intelligent? And wow, is that a big question. And now that we know we can actually do it, there will be people that will do it. And it does make a great deal of difference what the lawmakers decide. The perhaps more important aspect of this is that, to draw a comparison, at the moment, everybody writes programming languages and operating systems, and it's an awful long way from Juncker. If you actually were to take a computer and print out a program, it would be extremely difficult to work out what it did. You would know. Therefore, it's still extremely difficult to work out how DNA works. The point is, we can now read program. And nearly all science, it starts as science fiction, and everyone's blah. And then someone actually shows you that you probably know, what's that one for the expression, beam me up, Scotty? Everyone's, oh, there's rubbish. Well, I don't know how many of you have seen teleportation, but I've certainly seen an example of teleportation. Admittedly, it was only transmitting one molecule from one side of the laboratory to another, but it was teleportation, so that is technically possible. It might take a little while before you can actually transmit a person, or even perhaps one cell. So, one has the impression that we're standing on the brink of a huge expansion of human knowledge. And if you look at it, it's almost entirely dependent, that huge expansion, on the fact that we've got computers. Talking about DNA, would we have been able to analyze DNA if it hadn't been for computers? And that's one side of it. The other side is that, thanks to word processors, everybody can publish in papers. And if a publication won't publish them, then you can go and put them on Cornell's archive file. I'm sure you all know that. The last time I looked at 130,000 papers. And luckily we've also got a tool for us to hunt down who wanted to read. So we've both got the means to communicate from both sides. And that actually hasn't really been true before. If you read Alan Turing's original paper in 1936 to the Royal Society, there are 14 typos, and crossed out and something's written in because the secretary made a mistake typing. Presumably there were an awful lot more earlier, and he just gave up on the last 6 corrections, but there were. There are many ways in which computing is turning our world upside down. Now let's look at it from another point of view. If you look at very nearly every invention that you can think of, going right the way back to the plough, wheel, all the way through to the Industrial Revolution. Steam engines. And interestingly, we built the steam engine before the scientists had any idea of the laws of thermodynamics. Science had to follow the machines. And then, of course, electricity. Every one of them had an effect as a supplement to our muscles. We had these machines, and we made a show this morning, Peter, that although you flew in from these, there was no sign of you growing any things. And evolution, I suspect, was that rather long, but there's absolutely no conceivable way, there's no pressure on evolution from our invention. There's no reason why we reject it. Now, we've had machines of one sort or another, inventions of that sort, well, for at least 3,000 years. And we had the Olympics, more or less, for 3,000 years. Human beings actually aren't any stronger. We might be able to run a little bit faster, jump a little bit higher, but it's very not. So all our inventions, wonderful as they are, have not actually changed human beings. They have done very, very things for us. In any sense of criticism, but it's not what computers can do, because computers actually can support and help whatever we're going to use. Our brains. They're the only other machine in existence that can process information. That makes them unique, if nothing else. But already in such a short space of time, we have things like or all the rest of it. We're right on the cusp of having the entire body of human knowledge, art, culture, on our computers, in our pockets, or wearable, in due course, plugged in, the lot. I'm sure lots of people say, yes, well, Wikipedia has got mistakes in it. Well, there are a fair number of mistakes in the Encyclopedia Britannica that was published 100 years ago. And what was wrong in that was that they stayed wrong for the entire time somebody owned them. With all our electronic systems, of course, we can update them. We can do a lot more now. Because not only have we got raw information, but I'm sure you've all been reading about the online school and university courses. You can now actually watch a video of perhaps the best teacher of a subject, actually give a lecture presentation on their subject. Now, that isn't working too well at the moment, but it's a start. As Stanford have done some very interesting work, as many of you I'm sure have seen. And generally speaking, if you watch a video, you come up with a question, you haven't quite understood that. And if in fact you buy your course, you put it on, and you tap in your question, you get the answer from the chap who gave the lecture in Q. Now, everyone says, how's that? I mean, that poor devil who gave the lecture is sitting there in Stanford waiting for the questions. Well, of course he's not. And the computer literate world knows that Stanford can work out what the most likely questions are. And you're asking question 42. Oh, we have 42 now. And so there's question 42's answer, and the system plays it back. But look at the change. We can go further. One thing that the whole of cognitive neuroscience, and certainly the educational community, has never studied, because it's really quite complicated, is that every one of us has got a different type of brain in exactly the same way as everyone has got a different retina. Everyone has got a different brain. And there's a lot of argument that they cluster. It used to be fashionable to talk about left brain, right brain. I think that's slightly out of fashion at the moment. But there is a lot of solid evidence that some people are much happier, as it were, thinking in mathematical terms or logical steps because they're more comfortable that way. And there are other people who, one might argue, are more on the literate side, tend to think, we would say, more like an analog, because they think in terms of, if they're writing something, the emotional effect of what they write. And there are a lot of people in the middle of it, and maybe not necessarily one thing or the other. But there's no doubt that there are different types of brain. We can now, therefore, write MOOCs. It's a terrible word, isn't it? What's it go? Multiple online, what's the next systems for these online systems. You'd think we could think up something better than the word like MOOCs, but still. You can actually write them now for different types of, if it's children learning maths, or if it's older people who don't know what they're doing. So you can actually, if it suits some young people who are looking to, or students of any age, you can actually write the course to suit the way they like to think. And if they like to think in the traditional way, if it's written on the blackboard and they can see it, fine. For the other lot, maybe you have cartoons, and you have your favourite cartoon of your favourite character, who says, "Hi Charlie, what are you doing today? Let's all do so and so, what about who, etc., etc., etc." If that's the way they like to learn best, great. There's a lot in the paper at the moment about the fact that British are illiterate, or young people are illiterate, which is of course a load of rubbish. There's an interesting experiment that's going on, I believe, in Finland, where one teacher, I understand, has a class from the first day the kids go to school right through to whatever they have in place of GCSE. Because they reckon that means that we can see it in Egypt, some potential advantages. What about the kid that doesn't get along with his teacher? Now, all of us had to suffer school at one time or another, for a longer or shorter period. And there were teachers that you felt comfortable with. And there were teachers that you, oh God, what are they doing? And if you got on with the teacher, it was amazing how much better you were at that subject, etc., etc. If you didn't get on, you didn't. Now, that is something that the educational world really don't like, because they say that a professional teacher must be aware of this and therefore compensate for that. Or maybe it would be much, much more sensible, I think. I've always thought it would be much more fun if children selected their teachers, as in fact people do, for learning. There wasn't. If they're learning music or something, they go along and find a teacher that can teach them the piano. Yes. Much, much better if young people, the teachers all line up and explain how they would teach maths. And the young people say, well, I think you teach me best. That's quite a long way away, I think, from the views of Her Majesty's government. It's right, it's me, it was me. But let's go on to how can we use our computers to actually help us and succeeding generations use our brains better. Because even though we've got the internet, we've got Wikipedia, we've got Google and all that stuff, they are to a certain extent still tools, aren't they? We use them to do whatever we want to do. Great, wonderful, huge step forward. Can we go further? Now, if we look at the problem of learning, there are 4 steps. First of all, there's information, isn't there? I'm going to learn anything unless we actually have some information to learn. That must be the first step, acquiring information. Second step is how do we remember that information? Because if we can't remember it from one day to the next, we aren't going to get very far. The third is, it's quite possible for us to remember things without understanding their meaning. There are plenty of people who can recite whole strings of words. I think they understand what they mean. So there's actually meaning. And then there is one step further, being able to use that information to learn something new. I'm interested to know how many people, when they were at school, and I was hoping there would be more students here to answer this question, how many people nowadays are taught at school how to remember? Oh, good, well, you did. Oh, well, I mean, extremely relieved to hear that. I noticed that quite a number of other people who haven't. And it might be that you went in the United Kingdom. And I would argue that the first thing you need to do after you taught people to read and write is how actually do I remember things? Because my brain is different to everyone else in the class. So let's look at those 4 things. How can computers in those 4 studies? Well, the information bit isn't so difficult, is it? Because there's this cornucopia of knowledge. If people are curious to pick up information from one source or another, and of course there's the television and all the rest of it. I think the younger generation knows more about the natural world now than anyone else in history, probably thanks to Attenborough more than anybody else, and those programs are very wonderful. And when you're sitting watching David Attenborough describe something to do with elephants, you learn an enormous amount without actually having to think about it. Of course, that's the best way to learn. So I would argue that the younger generation today are probably better educated than any time in history. So actually picking up the information is difficult. I think we should actually spend some serious time working out what information actually is, defining what information is, where it comes from, how we process it, and actually, as I say, to define information. Which, curiously, you'd think, well, that's dead easy, in facts and things. And then you start looking, and it turns out to be remarkably complicated. But that's relatively easy, and computers are doing that job. Memory. Now, how do we remember? What actually goes on in our brains to take in information so that we can store it in such a way that when someone asks us a question, we can recall it? And there are many, many theories, all known centuries, as to how to do this. Because people have, since the beginning of writing, I suppose, written on record, people have realized that to be able to remember information is absolutely key. The oldest example I'm aware of, from about 300 to 500 BC, known as the system of loci, which I imagine you all know. It's always put in sort of slightly apocryphal terms that this guy was having a party, a dinner party, and he was called out by two gods, I suppose, who told him to come away from the party, whereupon the roof fell in, killed everybody at the party. And he was able to tell everyone the next day the names of everybody at the party, like where they sat around the table. And since then, every generation, Cicero had a wonderful way, which is well published, of when he was making a speech, he had a series of keywords to remind him to say, etc., etc. It sounded pretty obvious. It probably wasn't that someone did it, then it was obvious. And all through history, there's a rather good example from the Middle Ages, where somebody or other was promoting a scheme that was related to various sexual things he did with his girlfriends, and he got told off by the Pope, because that really wasn't the right sort of way in which Roman Catholics should remember things. If we come up to the present day, of course, there's lateral thinking, John Stuart Mill came up with his various theories, and there are all sorts of people who've come up with theories. Now, one of the most interesting things of all these ideas, how can we find shortcuts and ways to help us learn? One of them is, as you're walking along the street, you think on that house, that's the first thing that you remember, and it's the second thing, and so on and so forth. And then when you get to the supermarket, you remember the first house it was sugar, and the second house it was butter, etc., etc., etc. That's a little bit frivolous, but those sort of theories people put forward. Now, when people put those ideas forward, believe them, and usually they're very strong characters, and they say, use my system, and you will never forget anything again. And they enthuse people, and they wear charisma, and they believe it. They really believe it works. And their acolytes, and the people they persuade, believe it, and it works. it really doesn't work for them. And then he passes on to other people, and then sort of gets diluted. And after about a couple of generations, what's the system that works? And there's a huge amount of evidence for that. It isn't just a minor phenomenon. I think that teaches us quite a lot about how the memory system works. Because, as we're all well aware, the brain is only a very small piece of our whole bodies, and we've touched on the immune system and various other things earlier today. There's the whole autonomic system which runs the shop. I think, Peter, it was you who mentioned that the brain does a large amount in the background, which, and as a result, we touched on the subject of consciousness and whether things were done. So I can put that on one side. The point is that our system is working all the time, flat out, managing the system. And in fact, the brain really only, one would argue, evolved to coordinate everything. It's only an information processor because it is organizing everything we do. Slightly different from a computer, which can only process information, and there's no connection to anything else. So, the way it seems that we learn is that a lot depends on how important that information is to us. If there's a crisis, and we badly need to remember something, we'll remember it. If it doesn't matter whether we do, we don't, we may or may not. Recall, if there's a crisis, and we need this information, and it really is a real crisis, we can't invent it, then the chances of us recalling something is far greater. Repetition, partly. We know that every time that we use a network, we strengthen it. In due course it gets insulated, myelinated, the synapses get stronger, the network gets bigger all the time. So that's by repetition. How do we create a memory for the very first time? I touched on this morning, but there is a theory that if you've got two neurons firing more or less at the same time, they link up. Don Head, we'll put that for you, and it came up with a rather nice short thing. Neurons that fire together, wire together.